Hi, so for today we're going to talk about mixture problems, mixing of non-reacting fluids, and this is still a part of the application of first order differential equation. So the very first thing we're going to learn here in terms of mixture, okay, problems of mixture in the application of the first order differential equation is that the rate of change of substance in a volume is equal to the rate of entrance minus the rate of exit. Mathematically, if we're going to put that into our differential equation, we have dx over dt is equal to the r sub I c sub I minus, that's the rate of entrance, minus r sub o c sub o, that's the rate of exit. Okay, where r sub I is the volumetric flow rate at the entrance, meaning that's how fast, okay, is the liquid with together with the solution is coming inside the tank. And C sub I stands for the concentration of substance at the entrance, wherein R sub O is the volumetric flow rate at the exit. Okay, it means that the liquid is also has a rate of exit and has a rate of entrance. Okay, and C sub O is the concentration of the substance at the exit, where C sub O usually is not given in the given problem. So we usually express C sub O, or the concentration of the substance at the exit, as X over V, where X is the amount of salt or the solution, okay, and V is the final volume of the solution at any time t. Okay? Okay. So we have this differential equation. The rate of change of the substance with respect to time is equal to the volumetric flow rate, again, at the entrance, R sub I. And we have the concentration of the substance at the entrance, C sub I, minus, okay, the rate of exit. R sub O is the volumetric flow rate at the exit, multiplied by C sub O, wherein that is equal to the total amount of the substance X over the volume at any time t. So the volume at any time t is given by this equation, wherein we have the volume is equal to the initial volume V naught plus the volumetric rate at the entrance minus the volumetric rate at the exit multiplied by time. Okay, so we have to familiarize ourselves with this and also with this. Okay, let's try to solve some problems. For number 1, a tank contains 200 liters of fluid in which 30 grams of salt are dissolved. Okay, so we have a tank that contains, let's try to draw a tank, okay? Or we can usually visualize this as this. We have the initial volume of 200 liters, and we have, okay, a solution X naught, okay, initial 30 grams of dissolved salt, okay? So, the second sentence tells us brine containing 1 gram of salt per liter is then pumped into the tank at the rate of 4 liters per minute. And the solution mixed well is pumped out at the same rate. So, there is a solution coming inside the tank, okay, wherein we have 1 gram of salt per liter. 1 gram of salt per liter, that is our C sub I. Okay, 1 gram of salt per liter. Okay, that is our C sub I. That's the concentration coming inside the tank. And we have into the rate at the rate of 4 liters per minute. So, it's coming inside at a rate of 4 liters per minute. Okay, 4 liters per minute. And the solution mixed well is pumped out at the same rate. So, meaning Ri is equal to Ro, R sub O, because pumped out at the same rate. So, R sub O is now equal to 4 liters per minute. Now, as you can see here, the C sub O is not given. So, how do you find that C sub O? So, the C sub O, as I've said a while ago, is usually X over the final volume. Okay? So, we remain X because that is the parameter that is changing. So, we denote X as what are we going to find later on, because that's the amount of salt. So, the V is, as I've said a while ago, V is V naught plus R sub I minus R sub O T. So, we have V is equal to V naught, okay, plus, since the solution enters at a rate at 4 liters per minute and also going outside at 4 liters per minute. So this is 4 minus 4 multiplied by any time t. We know that this would be 0 though. So the initial or the final volume would now be equal only to the initial volume because logic tells us the rate at which it is coming in is the same as the rate it is coming out. Okay? It is pumped in at a rate of 4 liters per minute and pumped out at a rate 4 liters per minute. So, at any time t, the volume inside the tank is the same. Okay? And our V naught or our initial volume is 200 liters. So, if we are going to substitute it on our equation, we have the x, that is still x because that's the amount of salt at inside the tank. Okay? So, we have V naught which is equal to 200. So, putting that in our equation, we have dx over dt is equal to r sub I, c sub I minus r sub 0 or c sub 0. So, we have dx over dt is now equal to r sub I. Let me drop the unit. R sub I is 4. Where we have c sub I is 1 minus r sub o is 4 also. And our c sub o is x over 200. Okay? So as you can see here, we can solve this differential equation. We have dx over dt is equals to 4 minus 4x over 200. Okay? So that is our differential equation. Okay? And furthermore, again, we can simplify this 4x over 100. So we have dx over dt is equals to 4 minus 4 over 200 is x over 550. Okay? So x over 50. So if we're going to solve for this, we have dx over dt. We have 200 minus x over 50. Okay? Cross multiply. If I'm going to cross multiply that is 50 dx over dt is now equal to 200 minus x. Okay? As you can see here, we are forming an equation that is linear to x. So, let me just multiply the both sides of the equation by negative 1. So, as I will be having a positive x here. So, we have negative 50 dx over dt is now equal to x minus 200. Okay? And by variable separable, okay, so we can separate this as dx over x minus 200 is now equal to dt over negative 50. I just do some algebra here so that I can perform variable of separable here. So, integrating both sides. So, if we integrate this both sides, so what will happen? Okay, in this, we have to let u as equal to x minus 200. Okay, if we let u is x equals to 100, we have the du is equals to simply dx. So, this is simply ln du over u. So, if we integrate that, that should be du over u. And now equal to, so I can factor out negative 1 over 50 into the denominator and leaving behind inside the integral the dt. So if I'm going to integrate this, this is ln of u is equal to negative t over 50. Notice that the integral of dt is simply t multiplied by negative 1 over 50. So it becomes negative t over 50. Don't forget the plus c. And of course, our u here is simply equal to ln of x minus 200 is equal to negative t over 50 plus c. So let me just rewrite. So our result of the integral is ln of x minus 200 is now equal to negative t over 50 plus c. So we have finished integrating. So what do we need to find? Let's go back to the problem. So the problem states as find the number of grams of salt in the tank at any time t in terms of minutes. So we have to find the amount of the salt inside the tank at any time t. So we are actually solving here for the value of x. Okay, if you're solving for value of x, we must isolate x. Okay, in this case, we must exponentiate both sides of the equation. Okay? So what will happen? We know very well that the ln or the natural logarithm would actually be cancelled. So we have x minus 200, okay, raised to e raised to negative t over 50 plus c. So we have x minus 200 is equal to e raised to negative t over 50 by loss of exponent multiplied by e raised to c. But we know that e raised to c is simply the constant. So we can have x minus 200 is equal to c e raised to negative t over 50, and transposing, okay, negative 200 on the other side. So we have c e raised to negative t over 50 plus 200. And now, in order for us to find the amount of salt at any time t, we must solve for the value of this given constant c. So using our initial condition a while ago that at time is equals to 0, okay? At time is equals to 0, the amount of salt inside the tank is what? Is 30 grams, okay? That is equivalent to 30 grams, okay? So if we're going to solve that. So upon solving, we have we have 30, okay, that is equivalent to x, is equal to c e raised to 0, okay, 0 over 50 is 0, plus 200, okay, e raised to 0 is simply 1, so we have 30 is equals to c, plus 200, and as we can see here, if we solve for c, c is simply 30 minus 200, and we have negative 170. So, our equation for the amount of salt at any time t is given by simply substitute the value of c here in our model equation. So, we have x is equal to what? Okay, I can put this first. So, 200 minus the c, which is 170 e raised to negative t over 50. Now, if we plug in any value of time here in minutes, we can solve the amount of salt at any time t given. Okay? So, for letter B of our question here, find the amount of salt in the tank after 5 minutes. So, at 5 minutes, okay, time is equals to 5 minutes, we simply substitute the value of 5 here. So we have x equals to 200 minus 170 e raised to negative 5 over 50. Okay? So if we substitute that to our calculator, we will be getting an answer that is equal to 46.18 grams, at least to 2 up to 2 decimals. So that's how we solve, okay, the mixture problem. First, we need to identify the given parameters or the given, okay, the Ri, the Ci, the Ri, R sub O, and C sub O. Okay, and always take note that the C sub O is usually not given. We can find it by this formula X, the amount of the solute or the solution, salt at any time t over the volume V at any time t using this equation. Okay, and upon solving that, you need to separate some variables. In some cases, there are linear, okay, equations. Okay, so let's try the other example. Okay, number 2. Brine containing 3 pounds per gallon of salt enters a large tank at a rate of 2 gallons per minute. Okay, so as you can see here, upon reading the first sentence, okay, or the first phrase, 3 pounds per gallon of salt enters. So 3 pounds per gallon of salt, that is C sub I. Okay, at a rate of 2 gallons per minute, that is R sub I. It enters at a rate of 2 gallons per minute, and the mixture, well stirred, leaves at, okay, it is leaving at 1.5 gallon per minute. It leaves. This is a rate, so that is R sub 0. Okay? So, if the tank initially contains 100 gallons of water with 4 pounds of dissolved salt, letter A, find the amount of salt in the tank at any time t in minutes. In minutes. So, let's draw first, okay, a simple illustration of what's going on here. So we have initial volume of water is 100 gallons, and we have initial dissolved salt of 4 pounds. Okay? And we have R sub I, again, we have R sub I, C sub I here, and we have R sub 0, C sub 0 here. So our R sub I is 2 gallons per minute, and we have C sub I concentration as 3 pounds per gallon. And we have R sub 0 here, it leaves the tank at 1.5 gallons per minute. Okay? And our C sub O is not given again. So, again, we're going to find that C sub O by this formula. Okay? By this formula, our C sub O again is X over V, where X is the amount of soap at any time T and V is equal to this. So, we have V is equals to V naught, V sub naught, the initial volume of 100 plus the rate of entrance, okay, is 2 gallons per minute, and the rate of exit is 1.5 gallons per minute multiplied by time. Now, our V would be 100 plus 0.5 T. Okay? 100 plus 0.5 T. So, and again, what will happen? Our C sub O would be, okay, X over 100 plus 0.5 T. Again, our X here is still the variable that is changing. That is the amount of salt at any time T. So, at any time T, the value of the salt is changing, okay, here in our mixture. So, putting that into our equation, again, differential equation is dx plus dt, or dx over dt, r sub I, c sub I minus r sub 0 or c sub 0. So we have r sub I is 2 gallons per minute multiplied by c sub I, that's 3, okay, pounds per gallon of concentration, minus r sub 0 is 1.5 multiplied by c sub O, which is x over 100 plus 0.5 t. Okay? So we can multiply that. So we have dx over dt is now equal to 6 minus 1.5x over 100 plus 0.5 t. So as much as possible, I would not want to have a decimal right here. So what I'm going to do is that if I'm going to multiply it by 2 over 2, okay, 1.5x over 100 plus 0.5t. This is still equal to 1, okay? So it doesn't matter if I'm going to multiply it. So just to eliminate the decimal, so we have 2 times, we have 3x over 200 plus t, okay? So that our equation is free from decimal. You can do that, okay, because you did not violate any rule, because we simply multiply it by 1, 2 over 2, okay? So, continuing in our equation, I can transpose this on the other side of the equation such that we have 3x over 200 plus t, it became positive, is equal to x. And if I am going to isolate x, dx over dt, okay, plus 3 over 200 plus t, okay, multiplied by x. Okay, I just rewrite this, okay. So 3 over 200 plus t multiplied by x is equals to 6. This is linear in x. Okay? So our formula would be, by this, you should know already how to write the linear. So we have x e raised to p of x, which is 3 over 200 plus t. Okay? And with respect to dt, with respect to our independent variable t, is now equal to the integral of q of x, which is 6, okay, e raised to 3 over 200 plus t, that is the same term here, dt, and this is also evaluated in terms of t, with respect to t. So, as you can see here, if we're going to integrate this, okay, I can rewrite this as e raised to integral of, I can factor out 3 outside. So we have 3 over 1 over 200 plus t dt is now equal to, I can factor out 6 outside of the integral sign. And here, I can also factor out 3 outside of the integral sign over 1 over plus 200, 1 over 200 plus t dt, and I have dt here. So, I'm going to get the integral of this. This is simply e raised to 3 integral of dt over 200 plus t, okay, is equal to 6 integral of e raised to 3 integral of dt over 200 plus t dt, and I have dt here. So, if I'm going to integrate this, this is simply ln, okay? So, we have x e raised to 3 ln, okay, of ln of 200 plus t. Okay, 200 plus t. So, because if I'm going to let u is equal to 200 plus t and get derivative, that is simply dt. So, we have du over u, that is simply ln of u, of which our u is 200 plus t. Okay? So, we have equal to 6. The integral of, this is the same. So, this would be the same. E raised to 3 ln of 200 plus t. And we have dt in here. So, we all know by properties of exponent, I can rewrite this left side of the equation as properties of natural logarithm. We have e raised to ln of 200 plus t cubed. Okay, this becomes the exponent. And we have 6, the integral of the same, ln of 200 plus t cubed. Okay, and d. So, we know that this would cancel out. So that we have now x, okay, multiplied by 200 plus t raised to 3 is equal to 6 integral of 200 plus t cubed dt. And if I'm going to integrate this with respect to t, I can let u as 200 plus t, okay, du is simply equal to dt. So, u substitution. So, what will happen? X is multiplied by 200 plus t raised to 3 is equal to 6. The integral of u raised to 3 du. Okay? So, we know what will happen. X 200 plus t cube is equal to 6. Okay? U raised to 4 over 4 plus c. So, we have now x multiplied by 200 plus t raised to 3 is 6 over 4, that is 3 halves. Okay? That is 3 halves. U raised to 4, what is our u? By the way, our u is 200 plus t. So, 200 plus t raised to 4 plus c. And if I'm going to isolate x, okay, divide both sides by, if I'm going to divide both sides by 200 plus t cube. So, what will happen? X would now be, okay, so x would now be, so we have 3 over 2. So, this would cancel. This would be, we'll be having 200 plus t already here because of this cube here. So, we have plus c over 200 plus t raised to 3. So, this is the amount of salt at any time t in the tank. But still, we need to solve for the value of c. So, given the initial condition, okay, at time is equals to 0, okay, let's go back to our condition. At time is equals to 0, the amount of volume, okay, or the amount of salt is 4 pounds. That's the x, okay? So, the amount of salt is 4 pounds. X is equals to 4. So, what are we going to do is, simply substitute. We have 4 is equals to 3 halves, 200 plus 0, plus c over 200 plus 0 cube. So, as you can see here, 4 is equal now to 600 over 2. Okay, 600 over 2, that becomes 300. Okay, plus c over 200 cube. Okay? So we solve for C. We solve for C. What are we going to do? We have 4 minus 300 multiplied by 200 cubed is equal to C. So C therefore would now be, okay, we're just solving for C. Okay, we transpose 300, then we multiply both sides of the equation by 200 cubed. So we have C is equals to negative 296 multiplied by 200 cubed. Okay? So that would be our C. So therefore, the amount of salt at any time T inside the tank is equal to, let's go back to our general solution. So we have 3 halves. 3 halves times 200 plus T. Okay? Take note that C is equal to this. So C is equal to negative minus 296 times 200 cube over, okay, over 200 plus T cube. So we have 200 plus T cube. Okay, and furthermore, I can simplify this. Okay, notice that we have the same cube. I can factor out negative 296 outside. So that we have 200 over 200 plus T cube. And this would be our answer, that x is equal to 3 halves multiplied by 200 plus T, quantity 200 plus T minus 296 multiplied by 200, quantity 200 over 200 plus T cube. So this is the amount of salt at any time T in the tank. Okay? So we have to answer again the second question. The second question is that find the amount of salt in the tank after 4 minutes. So what are we going to do? Simply, after 4 minutes, we're going to substitute the time 4 minutes. X is equals to 3 halves 200 plus 4 minus 296 multiplied by 200 over 200 plus 4 minutes cube in our equation. And if we're going to plug this in, okay, in our calculation, this is at time is equals to 4 minutes. Okay, what is the amount of salt? Okay, so plugging this to our calculator, we can solve for the amount of salt after 4 minutes as 27.073 pounds. That's the amount of salt after 4 minutes. Okay, so I hope you learned something today in our lesson about first order differential equation, the mixing of non-reacting fluids. So that's all for today. Thank you so much for listening and God bless you.